Hello friend, welcome you all in this lecture number 8.1a. The title of this lecture is Density of States. This is the part of unit number 8 and which will be used further in unit number 9. That's why I am just including this lecture first. So this is also the part of this CSBT physics. Learn with me. Lectures on some special topics. So I, Dr. Mohan Verma, Department of Applied Physics, SSGIC Sankaracharya Technical Campus. Outlines of lectures are objectives and the prerequisite for the lectures. Where does the density of state concept come from? And then the derivation of density of state concepts, followed by these steps. First, an electron trapped in energy well with infinite potential, 1D and 3D calculation, K-space, concept of Fermi surface, and the final form of the output of this density of states, and the summary. So objectives and the prerequisite. The objective of this lecture is to explain the concept of density of states in detail, and the prerequisite to understand this lecture properly is that I expect the students should have the knowledge of basics of quantum physics calculation and energy levels, Fermi levels, and trigonometrical use of trigonometrical functions. So where does the density of state concept from? So let's define. First of all, let's include the definition of this. The density of state is essentially the numbers of different states at a particular energy level that electrons are allowed to occupy. Conceptual term is this, that is, the numbers of electrons per unit volume per unit energy is known as density of state. So in order to calculate the density of states, we follow the following approach. First, we find the smallest volume of K space. What is this K space? We will detail later. So find the smallest volume of K space that can hold an electron. This will turn out to be related to largest volume of real space that can confine the electron. The next, we assume that the average energy of free electron, that the Fermi energy E, this corresponds to wave number kf. This value of kf defines a volume in the K space for which all the electrons must be within. We then simply take the ratio of the total volume needed to account for the average energy of the system to the smallest volume able to hold an electron. That tells us the numbers of electrons. So this is the approach following three points, and from this we can differentiate to get the density of state distribution. So the derivation of density of state. First, we will start from the concept of electrons inside this quantum wheel, and this is similar to that particle inside a box where the size of this box is 0 to a in one-dimensional case. So again, we will start from that Schrodinger equation. So this is the Schrodinger equation, and in one-dimensional case, one can write this Schrodinger equation like this: that h cross square by 2m del x square psi by del x square minus e psi it is equal to 0, where this psi is the wave function. So by putting this by k in place of this energy and 2m by h square term, we can rewrite this relation like this. So the solution of this equation is generalized as psi x is equal to a sin kx plus b cos x, and where this k is 2 pi by lambda, and this k is also written as 2 m e by h cross square, or in terms of e we can write this e is equal to h cross square k square by 2m. So this is a simple calculation. Now we have this boundary condition. This psi, the wave function psi is 0 at this x is equal to 0, as well as at the boundary x is equal to a. So first, by using the first boundary condition, psi is 0 is equal to 0, b will be 0 because this cos 0 is 1, so this b will be 0. So finally we will have this psi x is equal to a sin kx, and when we put the second boundary condition, x is equal to a, then psi a is equal to 0. So a sin k is equal to 0, and this implies k is equal to n pi by a, for n is equivalent to plus minus 1, plus minus 2, plus minus 3, and so on. And further, when we put this k is equivalent to n pi by a in this relation, we have this energy value En is equivalent to n square pi square h cross square 2ma, and that wave function psi can be written in this form: psi nx is equivalent to n sine n pi x. So here, what is the meaning of this? This is that wave function psi, which is actually a standing wave, results from the requirement that there will be node at the barrier edge. So here, there one node is here, so in the barrier there will be different nodes at a different value of n, and these are different discrete energy values for n is equivalent to 1, 2, n is equivalent to 3, and n is equivalent to 4. By putting the value of n here, we can calculate the value of energy, and one can say this is the representation of wave function psi, and this is that the probability density which we used in quantum physics, that psi square, which gives the probability of existence of a particle, or that in this case an electron, and a particular energy level. So here that probability is maximum. When we take this n is equivalent to 2, there will be equal probability here in these 2 points, and in the case of n is equivalent to 3, there are 3 points where the probability of existence of that electron is more, and so on. So many different possible states can be occupied by the electron, each with different energies and wavelength. So these are different states where electron can occupy. So this is that wave function psi, and one can generalize this En is n square pi square h cross square 2 m pi a, and classically we have this is proportional to k square. So we must have one parabolic curve, that solid curve, but here what we are observing is that E energy value has the discrete energy levels, and these are that discrete energy levels. So the energy values of our confined electrons are quantized. We have taken this as a discrete. Note that at the dimension of the energy well increases, the spacing between discrete energy levels reduces. In this infinite crystal, a continuous same as our free particle solution is obtained. So this is for the free particle of a crystal, and this is the discrete energy level for different k values. Now the general form in the three-dimensional case. So this is that Schrodinger equation. This is the one-dimensional case when we put y and z coordinates again. So we will have this three-dimensional Schrodinger equation where this x is less than or equivalent to confined in between 0 to a, y is confined in between 0 to b, and z is arranged in between 0 to c. Here this k is equivalent to pi by lambda. Obviously the same formula we have used in the one-dimensional case. So the solution of this partial differential equation, we use a separation of variables method, where this xyz, psi xyz, it is written in the multiplication of separate parameters corresponding to x, y, and z. So by putting this value, these equations can be rewritten like this, and separately this can be compared with kx square, this can be compared with ky square, and this is compared with kz square, and where this k square is equivalent to kx square plus ky square plus kz square. So this is the simple methodology used in different solution of differential equation. So now this psi xyz can be written as equivalent to, this is for x-axis, this is for y-axis, and this is for z-axis solution. So a sine kx, ky y sine kzz, where this kx is equivalent to n pi x, ky is equivalent to n pi y, and kz is equivalent to n pi z, and so on. So here in place of kx we have ky and kz in the similar manner. So for each solution, each combination of nx, ny, and z results in the volume of k space. Here this k space is actually the momentum space, and each x, y, z axis is replaced by the corresponding momentum. So far we have this simple three-dimensional coordinates corresponding to x, y, z, but here we will use in k space and as kx, ky, and kz in three-dimensional case. So if we add all the possible combinations of this nx, ny, and nz, we would have an infinite solution. Thus we will simply only consider states confined in a Fermi sphere. So you will not including all these combinations of nx, y, and nz. So we will start another concept related to that Fermi space, but before this, the volume of single state, that is the cubic state, that volume is this is pi by a, n is equal to 1, kx multiplied by ky multiplied by kz. So this is pi by a, pi by b, pi by c. So that is equivalent to pi square, and a, b, c can be written as equal to capital B, where this V is the physical volume of crystal, whereas all other volumes used here refer to volume in K-space. Note that V single state is the smallest unit in this K-space, and V single state is required to hold a single electron. So V single state corresponding to a single electron, and here this V is for that K-space as a whole. Now for the Fermi sphere, it is defined as by the numbers of states in K-space necessary to hold all the electrons needed to add up to the average energy of the crystal, and that energy is known as Fermi energy. And this is also defined as the momentum value for the average electron energy. So EF, this is the Fermi energy, that is equivalent to h cross kf square by 2m. So this kf, that is the outermost surface of that K-space. So K-space volume of single state cube, this we have calculated, so that is pi square by V. And K-space volume of Fermi sphere, it's just a sphere, so we'll use the formula that 4 pi by 3 pi kf cube, where this kf is the radius of that Fermi sphere. Now the numbers of filled state in a Fermi sphere can be calculated, represented by n, and it is calculated by using this formula, where this is the volume of Fermi sphere mentioned here, and this is the volume of single state, this is calculated here, and these are some additional parameters. These two corresponding to 2 electrons per state. So by using that Pauli's exclusion principle, we know that in each level there will be 2 electrons, and there is half multiplied by half multiplied by half, that is 1 upon 8. This is why, because we are using one single positive octane only in the Fermi sphere. So this is corrections for redundancy in the counting identical state resulting from this positive negative values of nx, ny, nz, and we know that sine minus x is equal to sine sine minus pi is equivalent to sine plus pi. So we just use only the single octave of that Fermi sphere. That's why this 1 upon 8 is used here. So the final calculation, so this 1 2 can be cancelled, and this is that 4. So 4 pi by 3 pi kf cube upon pi cube by phi. So we will have this now. So 4 can be cancelled here. So b kf cube by 3 pi square. This is the value of n, which is the number of filled state in this Fermi sphere. Now further we can calculate it for kf. So this kf is equivalent to, just shift here, so this is 3 pi square n by v to the power 1/3, and this kf is required to calculate this Fermi energy EF. So EF is equivalent to h cross square kf square by 2m. So this is equivalent to h cross square, and by putting this kf from this, we will have this 3 pi square n by v to the power 2 by 3 upon 2m. So finally, if we want to change this n upon v as n, small n, that is the electron density, then this EF is equal to h cross square 3 pi square n to the power 2 by 3 by 2m, where this EF varies from 0 to 1, 0 to 1.1 electron volt for silicon, and n, this electron density, that is in between 0 to 5 into 10 to the power 21 per centimeter cube. And this n, from this relation we can calculate in terms of kf. N is equivalent to b kf cube by 3 pi square, where this kf can be also written as equal to 2me by h cross square. So this v by 3 pi square, and this is the final term for this n. Now final calculation of density of state function. So this n in terms of f we have calculated in the last slide, and this density of state is finally defined as represented by GE. This is the state per energy per volume. So that is equivalent to differentiation of n upon dE by upon the total volume. So we have this value of n. We can take the differentiation with respect to e. So let's differentiate this. So this is 3 by 2, so there will be 3 by 2 in multiplication here. B by 3 pi is constant, so this is 2m e by h cross square with minus n, that is half, and then this it is multiplied by 2m by h cross square, and it is further divided by v, so v can be cancelled here, and finally ge is equivalent to m root of 2m by pi square h cross square root of 3. So this Fermi density of state is directly proportional to square root of E. So applying to this for the semiconductor, we must recognize this m as m tends to m star, which is actually the effective mass of electron or effective mass of that hole, since we have only considered kinetic energy, not the potential energy now. So this E can be also replaced in semiconductor physics, that E tends to E minus EF, and for semiconductor we will have this relation G is equivalent to m star root of 2m star by pi square h cross square root of E minus AC. So we will have this relation in different form depending on different books. So the final form is this. So now the summary. So in this lecture, the concept and calculation of density of states were discussed in several aspects. So first we have introduced that case space, Fermi sphere, and then just to take the volume for a single electrons and divided by that that the volume of Fermi sphere is divided by that case space for the single electrons, and then we have included two more terms, and by differentiating that we can finally calculate that density of state. Thank you all. So for the detailed calculation, please follow in that green board session of this lecture.